the moment you've all been waiting for, the difference between resistance and resistivity. So here it is. Resistivity, and I will go ahead and write this over here. Resistivity is a property of the material. It is a property of a material. It means that no matter what shape, size, length, area, width the material is, it'll always have the same resistivity. If I have a pound of copper or just a gram of copper, it has the same resistivity, okay? This is different from resistance, which depends on the actual geometry of the object. So resistance depends on size and shape. Okay, that's key, because if I have a pound of copper and a gram of copper, the resistance is going to be very different. If I have a gram of copper and it's a cube versus stretching it out into a wire, it'll have a different resistance, all right? And the way that we can find the resistance from the resistivity is by this simple relationship. And that relationship is that the resistance equals the resistivity times the length divided by the area, all right? Simple as that. We take the resistivity, we multiply it by the length of the object, right? That in the direction that the electrons are flowing, divide it by the cross-sectional area. So in other words, if I have a wire like this, right, this would be L, and then this here would be A. All right, so in other words, the longer an object is, the more resistance it has. That makes sense. There's much more length that the electrons have to actually move through, all right? And the bigger A is, right, the smaller the resistance is going to be, which makes sense because if you have more area for the electrons to flow through, there should be less resistance, right? There's more room for those electrons to be flowing, okay? So I say here, I realize that is a questionable thing to say, but the truth of the matter is that the best resistors are tall, right, in other words, long, thin, right, so that's small area, and hot, which we know from the previous example that resistivity increases with temperature. So there you have it. The unit of resistance is the ohm. And let's do an example. Let's find the resistance of a certain object inside your actual body. What object would that be? Why not a bicep? Let's just take a bicep, okay? All right, so again, this is our formula for resistance. It's rho L over A, okay? And so a couple assumptions here. The resistivity of skeletal muscle is about 17,000 ohm meters. So rho for muscle is 17,000 ohm meters. So that helps. That's just going to go there, right? Okay, using this fact, let's approximate the resistance of your bicep. And so we have some decisions to make. First is, what is the length of a bicep? Okay, I mean, if it's this length right there, I don't know. I would say on the average person, it's probably about 10 centimeters, right? So from here to here, I always think 10 centimeters is the length of a Campbell soup can. And if I were to take a Campbell soup can, it would probably fit there just perfectly. So that would be 17,000 times a length of 10 centimeters, which is 0.1 meters. All right? Okay. And so as far as the area goes, as far as this fellow goes over here, we have to make a little bit of an assumption. All right? The assumption is, what is that cross-sectional area? And in order to find the cross-sectional area, we need to think of what actually is the shape of a bicep. And, you know, I just said a Campbell soup can a little while ago, and it's not perfect, but I would say to the best approximation, you know, the bicep is kind of a cylinder, right? It's round, which would mean that your area would be a pi r squared, right? The cross-sectional area of a cylinder is a circle, and so that's just pi r squared, all right? Which begs the question then, what is the radius of that cylinder? And I made an approximation here. I said that it would be about a 3 centimeter radius. All right. Maybe that's a little bit on the bigger side of biceps, but let's all be hopeful about our bicep size. All right. So let's go ahead and call this 0.03 over here, 0.03 centimeters for the radius of the bicep. And if I put all that in, okay, I get a resistance of 6 times 10 to the 5 ohms. Okay, and I will go ahead and say that is a pretty high resistance. Most of the resistors that you see that we will use in circuits will be in the thousands of ohms. This is almost a million ohms. So that that can be explained by the fact that your body is a conductor, right? You can conduct because most of it's actually made of water, but it's not a great conductor. In fact, it has still a resistance of 6 times 10 to the 5 ohms. As we move on in the course, we're going to talk more about how you can actually solve for a current, how strong the current is based on that resistance. All right? But the bottom line is here, our body is a conductor with its own resistance. We can almost treat it like a circuit. And that's why it's valuable to learn this stuff. Maybe if you have played with resistors at some point, you saw that there's these little stripes on the resistors. I just wanted to take a moment to explain those. The color and the order of those stripes gives you essentially the strength of the resistance. All right, and there's a little code here that explains. So the first color is the value of the digit, and the second color is the value of the multiplier. So, for example, if you see red then brown, that'll be 2 times 10 to the 2 ohms. Sorry, 2 times 10 ohms, right? And so that would just be 20 ohms if you have a resistor with a red then a brown stripe. And you could go ahead with any color combination and draw the same conclusions just using this simple setup. Honestly, that's more on the engineering side of things, but I just thought it was important to explain why the classic resistor has those stripes and how you could determine the resistance from those stripes. I also want to draw attention to another classic example of where resistance shows up in the body, which is, again, neurons and nerves. Because, neurons and nerves are the conductors. They're the circuitry of the body. So just to read this really quick, this image here is of an electron microscope that shows the cross-section through a nerve fiber, which is about 1 micrometer in diameter. A layer of an insulating fatty substance called myelin is wrapped around the conductive material of the axon. You've probably heard about myelin. It's really, really important for cognition. And there's a lot of evidence that once myelin starts to degrade over time, that's when dementia sets in. Your mind isn't working quite the way that it used to. And the things that help preserve myelin, that resist myelin from its de-evolution, will actually cause you to be able to be sharper for longer. All right, something that will be very important for you with future patients to share with. And there's many, many things that seem to correspond with, dietary things and lifestyle things that correspond with stronger myelin around your axons. Anyways, the resistivity of myelin is much greater than that of the axon, so an electric signal traveling along the nerve fiber remains confined to the axon. In other words, your current, your electron, is not allowed to leak out because the resistance is so high. You can think of it just like a wire. When you have a copper wire, the inside's all copper, but the outside has that thin rubber or enamel coating. All right, that's basically just like the myelin of an axon in a nerve. It's amazing how us in our creating technology, we've had to mimic things that the body has already figured out how to do. And so bottom line is, this makes it so that the signal is able to travel much more rapidly and the signal gets to stay coherent. And if myelin degrades, you lose that signal. And if you lose your electrical signals in the brain, it's harder to function, it's harder to have memories. And yeah, Makes sense. I have a video model of how this all works that I'm putting in the module, so I would check that out after this video. And I would lastly like to, well, I think I'm going to call it there. That is what I'm going to share about the difference between resistance and resistivity. Once again, every material, no matter what it's shaped like, has the same resistance and same resistivity. And so the resistance is dependent on that resistivity and the shape and the size and the quantity. And you can relate the two with this little formula. Hope that makes sense.